we are going to change the instructions on this one to, instead of use a, to without a. Without a graphing calculator, graph y equals log 8 of x. So we have done this already. This is a parent graph for a log graph. All of our parent graphs for log graphs have some common characteristics. What's one common characteristic of a log graph? They curve. What point do they go through? 1 and 0. They go through 1 and 0. What's another common thing for all log graphs? X equals 0 as an asymptote. And if I were going to label another point, what would be the other point for this log graph? Yes, 8, 1. It's always going to be the base, 1. Because if you think about it, if I put 8 in for x, 8 to what power is 8? 1. And if it was a base 3 and you put a 3 in, 3 to what power is 3? Would be 1. So you're always going to have the point, the base, 1. And then there's the shape of your log graph. Does it have any intercepts? It only has an x-intercept at 1. The equation of the asymptote is x equals 0. The domain is bigger than 0. And the range is everything. Now, we have to be able to quickly draw the parent graphs of any log function because we are going to do the transformations that we did in Chapter 3 with all of our log graphs as well. Earlier in the unit, we did transformations with all of our exponential graphs, 2 to the x and 5 to the x, whichever base to the x, e to the x. And now we're going to do the same thing with our log graphs. So turn to page 400, because I think that's an empty page. And on page 400, we are going to do 2 graphs. Here is our first one. We are going to graph y equals 4 log base 3 of x plus 1 minus 5. So the first thing you need to do is be able to recognize what is the parent graph, the parent log graph in this case. It's going to be a log base 3 of x. And you're going to draw a quick sketch of that off to the side with your asymptote at x equals 0. Every log graph goes through 1, 0. And what point will this one go through? 3, 1. So we have our base graph, our parent graph off to the side. And the same thing that we did with our exponential graphs is also helpful for our log graphs because our parent graph has a number in it. And sometimes when you're moving left to right and you see a number, you think you have to do something with that number. So I'm going to go to my equation and I'm going to put a box around the log 3 and a box around the x just so I remember that those values aren't going to affect my transformations. So when I move from left to right, I'm only going to hit the 4, the 1, and the negative 5 as far as transformations. That 3 won't affect my graph. It just makes my parent graph. So now we can take our 2 points and our asymptote and apply our transformations. Moving from left to right, we are always going to hit our stretches and compressions first. So the 4 is going to multiply which coordinate? It's going to multiply our y. Y by 4. Are we going to multiply x by anything? No, because there's a 1 in front of the x. So we only have to multiply y by 4. And then if we do our translations next, we hit a 1. That's 1 to the left. And the 5 will be 5 down. So moving 1 to the left and 5 down, 1 to the left and 5 down, we get those points. What is the only thing that's going to affect this asymptote? 1 left. Moving something left and right is the only thing that's going to affect a vertical asymptote that starts at 0. So moving it 1 to the left, will get us to x equals -1. So putting that all together, we can draw the graph. Start with your asymptote. X equals -1. Label your points. We have 0, -5, and 2, -1. And remember, if you're making your own graph, it's important to actually label those points so that you indicate that each of these lines that you're drawing is going by 1. And once you have those 2 points, well, it's got to go towards the asymptote, so it's got to curve down this way. And I'll have the same shape as our logarithm graph did to begin with. So this reviews our transformations unit again. We just have new parent graphs to work with. For our second example, we're going to graph y equals 2 natural log of 1/2 x plus 2 minus 3. Now, there's 2 reasons I picked this one as our second graph. What are the 2 things you think I want to show you with this one? A natural log, just because the base is weird, it makes it a little bit harder. And it's only harder if you haven't ever done one. Once you've done one, you find out it's basically the same idea as any other log. So that's one thing I wanted to do with this one. What do you think another thing I wanted to prove? There's actually could be 3, but you have to factor out the half because it has a horizontal stretch compression with a horizontal translation. So before we even start recognizing that, and I'll use 2 sets of brackets, that half has to be factored out. And sometimes factoring out a fraction can be difficult. So what I find helps me or makes factoring out a fraction easier is instead of saying, oh, I'm taking a half out of 2, because you're sort of like, what? Take a half out of 2? It's easy to take 2 out of an 8, because you get 4, but a half out of 2 seems to be a little bit more difficult. So instead, what I think about is, well, if I take that half out, if I distribute it later, I should get this. So what number has to go in that second space? So when I multiply it by half, I get to 4. And so taking a half out of 2 gives you 4. And maybe it makes sense because if you think about a 2-liter bottle of pop and you wanted to take half liters out of there, how many would you get? You would get 4 of them. 4 or 500 ml bottles would come out of there. That's what taking a half out of 2 means. But sometimes when you just say take a half out of 2, without a context like that, the math just sort of goes, whoa. And so I find it is easier to think about distributing and what number would go in there. Now that we've done that, to graph this, we start the same way that we graphed our last one. What's our parent function? The natural log of x. What does it look like? Well, it has an asymptote at x equals 0. All logs go through the point 1, 0. And this one's going to go through the point e, 1. Has the same shape as all our other log graphs. Everything is good. Going to our equation, that means this and this are part of our parent function. But it's actually, we don't need to put the green box around that as much because the natural log has no number that appears, so you're not going to get confused with thinking that's part of one of your transformations. So starting with our 2 points, 1, 0, e, 1, and our asymptote at x equals 0. Moving from left to right, we have a horizontal stretch and a vertical stretch. We're going to multiply our y by 2 and our x by 2. Right, we have to remember that for our horizontal stretches, we multiply by the reciprocal. So we're going to get 2, 0 and 2e, 2. So even though there's an e there, you're going to multiply it by 2. Sort of going to act almost like that's a variable. And you just get 2e. Finally, moving left and right, up and down, the 4 is going to move us 4 to the left. The 3 is going to move us 3 down. So we're going to get -2, -3. The 3 down is not hard here. Well, maybe I'll need a little bit more space. You'll get -1. What am I going to write for the x coordinate here? 2e minus 4. Because we just need to subtract 4. And that's how you would leave it, as 2e minus 4. What is the only thing that's going to affect our asymptote? The 4 to the left, so our new asymptote is x equals -4. So now when graphing this, start with our asymptote at x equals -4. Start with a point that's nice, -2, -3. Now, how are we going to graph 2e minus 4? Well, we're going to have to do a little bit of estimation. Do you remember what e is approximately? 2.7 blah, 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 blah. 2.7 is enough for an estimate. Can you multiply 2.7 by 2? What would you get? 5.4. Can you subtract 4 off of 5.4? 1.4. So when we're estimating this, we're going to go somewhere between 1 and 2. And we're going to do 1.4 minus 1. And when we label it, we can still label it as 2e minus 4, comma minus 1. And we get our second point. Now, that's what makes this one a little bit more difficult, is getting a place for that point. Connect your dots, draw it towards your asymptote, and we've got our logarithmic graph. To practice parent graphs, we can do 7a. For practicing the other ones, we're going to do example 3 right now, and then we'll practice those as well.